This is video 10C. In this video, we're going to talk about what happens when heat is added to a substance, specifically phase changes. So two things can happen when heat is added to a substance. It can either increase in temperature or it can change its phase. So what is a phase change? Is a phase change physical or is it a chemical reaction? Here are all of our phase changes and our vocabulary that goes with each. A phase change is just that. It's something that's changing its phase. It's going from a gas to a liquid or a liquid to a solid. It's not a chemical reaction. If you melt ice, it's still H2O. It's still water. It didn't actually change the chemical nature of the substance. So make sure you're familiar with all of these terms. If you're going from solid to liquid, it's called melting. We're going to use this word, fusion, for this unit. If you have a liquid to a gas, you're either vaporizing or evaporating. We'll talk about the difference between those in the next video. If you're going from a gas straight to a solid, it's either desublimation or deposition. You may use either word. If we go backwards, a solid straight to a gas, dry ice does this, it sublimes, it's sublimation. Gas to a liquid, you see in the mornings in your car, is condensation. And liquid to a gas, you know it as freezing or solidification. We can use the word freezing here. Make sure you're familiar with all of these 6 terms and when the phase change occurs. Phase changes are a result of either an endo or an exothermic process. If it's an endothermic process, you are putting heat into it. So if you have ice, yes, pretend this is ice. If you have ice and you add heat, it's going to melt. If you have water and you add heat, endothermic, it's going to boil. If you have a substance like dry ice, you can go straight from solid to gas. What was that term called? If you forget, check back on the previous slide. Or you can have exothermic reactions, where the energy or the heat is taken out. If you have a gas and you cool it down, it's going to condense into a liquid. If you have water and you put it in the freezer, it's going to freeze into ice. Or, again, dry ice, CO2. If you have a gas, it can go straight to a solid. What's that term? Check the previous slide if you forget. Phase changes. This is a phase change graph. On the x-axis, we have energy. We can also consider this to be heat, or our Q value. And on the y-axis, we have temperature. So, we start out here, low energy, low temperature, in the solid phase. As I add energy, going this way, as I add energy to my solid phase, it's going to warm up, warm up, warm up, until it hits a point where it's going to start melting. It's going to remain at this specific temperature until every little last bit of it has melted. This temperature is obviously the melting point. Now I have a liquid. So if my solid, this could be ice, you heat up ice until it starts to melt. The melting point of H2O is 0 degrees Celsius. So it's going to stay at 0 degrees Celsius until all of the ice has turned into water. Why does that happen? Well, when you're changing phases, all of this energy here that you're adding is being used to break the intermolecular forces. You have no temperature change until all of those intermolecular forces are broken. Once every little last bit of it has melted, now I can increase my temperature again in the liquid phase. My temperature is going to increase from 0 up to, this would be the boiling point. The boiling point of water is 100 degrees Celsius. Once I hit that 100 degrees Celsius, it's going to stay at exactly 100 degrees Celsius until all of my liquid has boiled into the gas phase, into the vapor phase. Staying at 100 degrees Celsius, constant temperature, 100 degrees is my boiling point, 0 degrees is my melting point. It will stay at this temperature while it's boiling, breaking again all of those intermolecular forces until I'm finally in the gas phase. Once 100% of it is in the gas phase, it can continue on and go above 100 degrees as a vapor. So your kinetic energy and your temperature are both increasing in the gas phase, in the liquid phase, in the solid phase. But when you're changing your phases, when you're melting or you're boiling, all of that energy that you're adding is being used to break intermolecular forces. So what does this really mean? Phase changes and enthalpy calculations. We can calculate exactly how much energy, if we're still talking about ice cubes, it would take for me to pull an ice cube out of the freezer, raise the temperature until it melts, raise the temperature again until it boils, raise the temperature even higher past its boiling point until it's a gas vapor. So, there's a couple equations that we're going to use. Whenever you have a temperature change, we're going to use our NC delta T equation because we have a delta T. Here I have a delta T in my liquid phase. This is solid. This is liquid. Here I have a delta T in my gas phase. But at the times where you're melting or fusion is happening, I have no change in temperature. So I can't use my NC delta T equation. I have to come up with another one. Delta H equals N. This is still your amount. This time it's usually in moles or grams. And your delta H fusion, again, is a constant given to you on your big data table sheet. So look for the specific substance that we're using, and you just pull this number right off here. This is usually in kilojoules per mole. No temperature change, so we don't need delta T. Same thing when I'm boiling or vaporizing. I can't use an NC delta T because I don't have a temperature change. It would make it equal to 0. So the heat of fusion is how much heat I need to vaporize 1 mole. So again, these units are going to be in kilojoules per mole. We'll have to watch our conversions. And then in the gas phase, again, I can use NC delta T because I do have a temperature change. So I'm adding heat. In terms of enthalpy, this is our delta H or our Q value. Change is not favored because we have to add energy. And the graph looks like this. It's an endothermic reaction. Here are all of our equations. Again, check your periodic table. All of these equations are present on your periodic table. You just have to know when to use them. Fusion is when it is melting. Vaporization is when it is boiling. And the Q, or the delta H, equals NC delta T, is when you are heating because you have some kind of a change in temperature. Now, this process, in terms of entropy, thinking back to our delta S, it is favored because I'm going from a solid to a liquid to a gas. And if you remember, gases are more disordered than liquids, and liquids are more disordered than solids. So I'm increasing my entropy. This change is favored. I'm moving towards much more disorder. So it's not favored in terms of enthalpy, but it is favored in terms of entropy. Let's try one. For simplicity's sake, all the data is given here. Make sure you know where I'm pulling these numbers from. So you'll have to look back on your data tables from your packet. Here's our big problem. Calculate the amount of heat, so delta H or Q, how much heat is required to convert 45 grams of ice at negative 22.5 degrees Celsius all the way to steam at 115 degrees Celsius. So let's label our temperature diagram. Way down here, you're starting at negative 22.5 degrees Celsius. Then, it looks like I'm going to heat up a little bit. I'm going to heat up to right here. This is where the ice is going to melt. If it's any substance other than ice and water, I'll have to give you a melting point. So your melting point right here for ice is 0 degrees Celsius. After it's completely melted, I'm going to increase the temperature again until it boils. Again, water boils at 100 degrees Celsius. If it's not water, I'll have to give you a boiling point. And then from the problem it says I'm going to continue to heat up my steam once it turns to steam until it gets to this point, and we're going to stop at 115 degrees Celsius. So, as you can see, this problem has 5 distinct parts. I'm going to heat it up, I'm going to melt it, I have to heat it up again, then we have to boil it, and then we're going to heat it up again. So there's 1, 2, 3, 4, 5 distinct parts. We're going to break it down into 5 distinct parts, and then we can add all those heats up, all of the enthalpies, to get a total amount of heat. Start with the first part. Delta H equals NC delta T. Again, I can use this equation because I have a change in temperature. So, delta H equals N. What's my N? N is in grams. I have 45.0 grams times C value. Again, check your data table. This will always be given to you. 2.01 joules over gram times degrees Celsius. And my delta T, I'm changing the temperature. Now, I only want temperature change for this first section. I'm going from negative 22.5 up to 0. So my temperature change final minus initial, 0 minus negative 22.5 is 22.5 degrees Celsius. So just for this very first part, you're going to get 2,035 joules just to melt, or just to take that ice cube up to where it's going to start to melt. Okay? Keep this number handy. In the second part, I can't use NC delta T because I don't have a delta T. So my equation changes slightly. This is my fusion equation because fusion means melting. Here's my number for fusion, but it's in kilograms per mole. So what am I going to have to do with 45.0 grams? 45.0 grams of H2O, I have to convert that to moles. The molar mass of water, 2 H's and 1 O, 18.02 grams. When you divide that, keeping 3 significant figures, I get 2.50 moles. That's going to be my N. 2.50 moles. And it's N times this constant, delta H of fusion, which is given as 6.01 kilojoules per mole. Moles cancel. 2.5 times 6.01, you get 15.03 kilojoules. So just to melt that ice cube from start to finish would take 15.03 kilojoules. Part 3. Now I'm in a liquid phase. I'm going to take it from the melting point to the boiling point. Since I have a temperature change, I can use NC delta T. So my N is still the same, 45.0 grams. The C value for water is 4.184 joules over gram times degrees Celsius. And now I want my temperature change, but just for this part 3. I'm taking it from the melting point up to the boiling point, from 0 to 100. 100 minus 0 is 100 degrees Celsius. Again, make sure your units cancel. Grams, grams. Celsius, Celsius. When you multiply this out, you should get 18828 joules. And now we've started boiling. Part 4, how much energy does it take to boil that now ice cube that's in the gas phase, liquid phase to gas phase? I have no temperature change, because all I'm doing is breaking intermolecular forces. So I have to use my N delta H vape. Why do I pick the vape? Because that means boil. My units are kilojoules per mole. So I'm not using 45 grams, I have to use again 2.50 moles. 2.50 moles times 40.7 kilojoules per mole. Again, my constant, make sure you know where this number comes from. Moles cancel. This section, number 4, takes 101.75 kilojoules of energy to boil that, what once was, ice cube. And our final state, number 5, since I'm increasing temperature again, I can go back to my NC delta T equation. My N is 45 grams. The C value for steam, or gas, is 2.01 joules over gram times degrees Celsius. And now for part 5, I'm changing the temperature from 100 to 115. 115 minus 100. My temperature change is 15 degrees Celsius. Section 5 should be 1357 joules, 1,357 joules. Now, I have all 5 parts done, but what did we notice about the units? Joules, kilojoules, joules, kilojoules, joules. In order to add these all up, we have to convert them into the same unit, all 5 pieces. So if we convert them all to kilojoules, we have, again, joules to kilojoules, you just divide by 1,000. 2 and let's keep 2 decimal places. This would be 2.04 kilojoules plus 15.03 kilojoules. That one stays the same. Plus, divide by 1,000, 1, 2, move it 3, 18.83 kilojoules. Plus, this one stays the same, 101.75 kilojoules. Plus, divide 13.57 divided by 1,000 equals, move it 3 places, 1.36 kilojoules. Now, when you add all 5 of these pieces together, you will get the total energy it's required to convert ice to steam from negative 22.5 to 115 degrees Celsius. And my answer is 139.01 kilojoules. Check that in your calculator, make sure that's what you get. And then worksheet 3 is going to be 2 of these practice problems. The only thing that I can change is the substance, so the melting point and the boiling point will change, but we still have our temperature scale. Keep it in Celsius. Always mark your melting point, always mark your boiling point. What if I start out with a gas and I'm cooling? So instead of the graph going up to the right, it's actually going to go down. If you're cooling, your temperature is going to decrease. So maybe I start way up here above the boiling point. My temperature is going to go down until it hits the boiling point. It will stay at the boiling point until it's cooled enough, and now it all has condensed. Once it's in the liquid phase, it's going to cool the whole way until it gets to the melting point or freezing point. It will then freeze into a solid, and if you wanted to, you could take the temperature even lower in the solid phase. So gases are still at high temperatures, liquids in between the melting and boiling point, and solids down here at the low temperatures. For one of these problems, your delta H is going to be a negative value because you're taking energy out of your system. It might be one of these. Let me know if you have questions. We'll try the worksheet problems when we come to class tomorrow.